1 minute ago, the ground beneath Alaska shattered in ways that scientists hoped they would never witness again. At 8:11 on Thanksgiving morning, a magnitude 6.0 earthquake ripped through the darkness, 43 miles beneath Susitna. The tremor jolted 300,000 Anchorage residents from sleep, throwing picture frames from walls and cracking drywall across hundreds of homes. In kitchens across the city, cabinet doors swung open, sending dishes crashing to tile floors. Car alarms wailed in unison as the ground heaved beneath parking lots and driveways. For those who had lived through previous quakes, the deep rolling motion felt different, more ominous than shallow tremors that strike quickly and fade. But the damage isn't what terrifies geologists. It's the pattern. The sequence of relative quiet followed by deep rupture carries echoes of March 1964 when a magnitude 9.2 megathrust tore through Prince William Sound, lasting 4.5 minutes and releasing energy equivalent to hundreds of nuclear weapons. That earthquake remains the most powerful ever recorded in North America, rupturing 600 miles of fault at once and generating tsunamis that killed over 130 people across Alaska, Oregon, and California. The ground rose 38 feet in some areas and sank 8 feet in others, permanently reshaping the coastline. Now scientists face a chilling question. Was this just an earthquake, or was it a warning? The seismic record shows something that makes veteran researchers uneasy. Before the Thanksgiving quake, Alaska had experienced a relatively quiet period for seismicity in the region. When compared to historical patterns preceding major ruptures, this lull could suggest tectonic plates locking in place, a process observed when stress accumulates before catastrophic release. The earthquake's characteristics, deep rupture combined with its proximity to the 1964 megathrust zone, raise questions about whether similar stress mechanisms might be at work. 50 days before the 1964 catastrophe, a magnitude 7.0 event struck southwest of Kodiak Island, an occurrence that only became recognized as a foreshock after the megathrust devastated south-central Alaska. Researchers studying that sequence found parallels between the foreshock mechanism and the main event, both involving thrust motion on the megathrust interface. Alaska Earthquake Center seismologists note that while each earthquake is unique, the depth and location of this event warrant careful monitoring. The pattern, though not identical, shares features with historical sequences that preceded devastating events. But there's something darker beneath the numbers. The earthquake originated approximately 70 kilometers deep within the subducting Pacific Plate, an intraplate event that radiates energy across vast distances. Its epicenter sat 12 kilometers west-northwest of Susitna, roughly 67 miles from downtown Anchorage. At that depth, the Pacific Plate bends and fractures as it plunges beneath the North American plate, subjected to immense stresses from both the weight above and the resistance below. This type of intraslab earthquake is common in Alaska, but the location matters. Even moderate quakes at this depth send shaking rippling through sedimentary basins where loose soils amplify ground motion in ways solid bedrock cannot. The Cook Inlet Basin in particular acts like a bowl that traps and intensifies seismic waves, extending shaking duration far beyond what the magnitude alone would suggest. Over 470,000 people felt the shaking. Nearly 185,000 experienced intensity level 5 tremors, the threshold where objects fall and structures sway noticeably. Yet official damage remained light. Toppled chimneys, cracked plaster, scattered belongings, no major structural failures, no tsunami. Emergency services reported only minor injuries. This was the largest quake to strike south-central Alaska since a magnitude 6.1 event in 2021. The real danger lies in what comes next. Within hours of the main shock, aftershocks began rattling the region, with the largest reaching magnitude 3.2. The USGS aftershock forecast assigned a 25% probability of a magnitude 5 earthquake occurring within the following week. But buried in the statistical models is a calculation that keeps seismologists vigilant. Based on historical earthquake sequences, there exists a small but measurable probability that this magnitude 6.0 could be a foreshock to something far larger. While such probabilities are typically low, any non-zero chance of a major event demands attention in a region with Alaska's seismic history. The possibility, however remote, that the ground could rupture again with enough energy to generate widespread damage cannot be dismissed. Scientists scramble to fill critical data gaps.
Full moment tensor solutions remain incomplete. High-resolution waveform data from distant stations are still being processed. Stress transfer models, the calculations that reveal whether an earthquake released tectonic pressure or simply moved it to a more dangerous location, have not been finalized. GPS strain data, showing ground deformation patterns across the region, are under review. Without these pieces, experts cannot determine if the quake relieved stress or if it loaded nearby faults closer to failure. The uncertainty is unbearable. Researchers can describe what happened, but they cannot yet say what it might mean. What they are watching now could determine everything. 5 indicators dominate the monitoring effort. First, aftershock decay patterns. If aftershocks cluster abnormally or fail to follow the expected decline, it signals rising stress elsewhere in the system. The rate should decrease following a power law, with frequency dropping predictably over time. Deviations from this pattern could indicate stress migrating to adjacent fault segments. Second, microquake behavior. Sudden swarms of tiny tremors could indicate fault segments approaching rupture. These events, often too small to feel, create patterns visible only in continuous seismic data. Third, fault coupling. GPS and satellite data reveal whether tectonic plates are locking more tightly, storing energy for a future release. When plates lock, the overlying crust bends and compresses, measurable as millimeters of horizontal movement and vertical uplift. Fourth, ground deformation. Subtle uplift or horizontal sliding detected by continuous GPS stations can betray stress redistribution invisible to human eyes. Fifth, magnetometer anomalies. Some researchers track electromagnetic fluctuations as potential, though unproven, precursors to seismic events. The mechanisms behind such signals remain controversial, but any repeatable pattern warrants investigation. A panel of experts will examine the full dataset within a week. The scientific community demands rigorous evidence before drawing conclusions. Theories about space weather influencing earthquake timing remain controversial. Some researchers noted that solar conditions aligned unusually well with the Thanksgiving quake, echoing patterns observed before other major seismic events. But correlation is not causation. Until a physics-based mechanism emerges, verified independently and proven repeatable, the connection remains speculative. What is certain is that Alaska's seismic behavior now mirrors setups seen before historical disasters, and one of the most frightening modern parallels comes from another volcanic giant on the opposite side of the world. Mount Etna has begun repeating a prehistoric nightmare. In early June 2025, a section of Etna's southeastern flank ruptured in a way that sent geologists into emergency mode. A pyroclastic flow, triggered by what initial observations suggested was a partial collapse of material from the northern flank of the southeast crater, sent tourists fleeing down the mountain as superheated gas and ash roared toward them. The event raised immediate concerns because the southeastern flank's geometry mirrors the collapse scar from approximately 8,000 years ago when a massive section of the mountain slid into the Ionian Sea, triggering a tsunami that devastated coastlines across the eastern Mediterranean. That ancient collapse involved an estimated 25 cubic kilometers of debris, enough material to cover Manhattan in a layer thicker than the Empire State Building, crashing into the sea at speeds exceeding 200 miles per hour. The impact unleashed waves reaching heights of 130 feet in some areas, racing across the Mediterranean at 450 miles per hour. Coastlines from Sicily to Israel felt the destruction. Archaeological evidence suggests the tsunami may have caused the sudden abandonment of Atlit Yam, a Neolithic village on the Israeli coast, where excavations revealed evidence of rapid evacuation, including gutted fish left to rot. The force of those waves reshaped seafloors across thousands of square miles, leaving sediment deposits that geologists can still identify today. Now, every modern warning signal matches that ancient catastrophe. The scar from that prehistoric collapse remains visible today as the Val del Bove, a massive depression on Etna's eastern flank stretching over 5 kilometers wide. The valley's steep walls expose thousands of years of volcanic history in cross-section, layers of lava and ash stacked like pages in a geological book. But the valley is more than a historical curiosity. It's a warning written in stone. The walls show that Etna's eastern flank has collapsed multiple times throughout its history, each event leaving behind evidence that researchers can measure and model. The current southeastern flank follows the same fault structures, sits on the same weak sedimentary basement, and shows deformation patterns remarkably similar to reconstructions of conditions before the ancient failure. Reports from June 2nd described a dramatic eruption that intensified around midday, producing what officials called a significant increase in volcanic tremor. Italy's National Institute of Geophysics and Volcanology reported that at 9:24 a.m., a pyroclastic flow occurred, likely caused by a collapse of material from the northern flank of the southeast crater. Field observations and monitoring data revealed elevated seismic activity, ground deformation consistent with flank movement, and ash plumes reaching several kilometers high. While the immediate event was contained to the summit area, the pattern of instability along the same southeastern flank that collapsed millennia ago prompted emergency protocols. Authorities responded with heightened vigilance. INGV maintains continuous monitoring of Etna through an extensive network of seismic stations, GPS receivers, tilt sensors, and gas detectors positioned across the volcano. Following the June eruption, officials restricted access to the upper slopes and intensified data collection. Satellite-based INSAR measurements track ground deformation with millimeter precision, revealing patterns of movement across the southeastern flank. The cumulative data from multiple monitoring systems paint a concerning picture. The flank continues its seaward slide, driven by processes that have been active for years. Based on decades of observations, researchers recognize the southeastern sector as the most unstable portion of the volcano. Not everyone living on Etna's slopes fully grasps the scale of the threat.
In neighborhoods near fumarole fields like Solfatara and Eerily, some residents have reported experiencing the volcano's restless energy firsthand. Walls that feel warm to the touch, mineral deposits creeping along baseboards, the sharp smell of sulfur that intensifies after rain. These are the daily realities for families living in the shadow of active volcanic vents. If you put your hand on the wall, it isn't warm, it's terribly hot, one resident described, her voice reflecting years of accumulated worry. Property values have declined in areas closest to fumarole activity, and some homeowners face difficult choices between costly repairs and uncertain futures. For those who remain, volcanic monitoring updates become part of the routine, another factor in daily life shaped by living on one of Europe's most active volcanoes. The financial burden compounds the uncertainty. Repairs to volcanic damage, from heat-resistant treatments to ventilation improvements, can consume thousands of euros. Insurance companies often exclude volcanic activity from coverage, leaving residents to absorb costs themselves. In some areas near active fumaroles, selling properties has become nearly impossible as buyers weigh the risks. Yet many residents choose to stay, tied to the land by generations of family history or simply having nowhere else to go. They watch steam rise from street cracks, monitor paint for signs of blistering, and adapt to a reality where the volcano has become an unwelcome presence in their homes and daily routines. The scientific explanation for Etna's behavior has shifted dramatically. For decades, researchers believed that magma pressure drove flank movement, pushing the volcano's eastern slope seaward. This model made intuitive sense. Volcanoes erupt, magma pushes outward, flanks slide. But in 2018, seafloor geodetic monitoring revealed something unexpected. A research team deployed 5 transponders on the ocean floor offshore from Etna's eastern flank, positioning them on either side of a major fault line. These instruments used acoustic ranging to measure positions with centimeter precision. The transponders recorded a 4-centimeter slip in just 8 days during May 2017. What shocked researchers was the pattern. Displacement increased away from the summit toward the coast and into the Ionian Sea, the opposite of what magma intrusion would produce. If rising magma drove the movement, the highest deformation would cluster near the volcanic center. Instead, the data showed maximum displacement at the coast and underwater, suggesting something else was pulling the mountain apart. Gravity, not magma, is pulling Etna into the sea. The volcano's eastern flank sits on an unconsolidated sedimentary layer that dips gently toward the Ionian Sea. This unstable foundation, composed of ancient marine clays, offers little resistance to the immense weight pressing down from above. The massive volcanic pile, over 2 kilometers thick, pushes downward with forces measured in billions of tons, creating a gravitational torque pulling toward the sea. The movement is continuous, relentless, measured in centimeters per year. Magma dynamics can accelerate the slide during eruptions, but the fundamental force is gravitational instability. This realization changes everything. If magma drove the movement, eruptions would be the primary trigger for collapse. But if gravity is in control, catastrophic flank collapse could occur without eruptive warning, triggered by tectonic shifts, earthquakes, or accumulated strain finally exceeding the strength of the rock. The implications are terrifying. Coastal and island volcanoes worldwide may face similar gravitational collapse risks, previously underestimated by models focused on magma pressure. Kilauea in Hawaii experienced a major flank event in 2018 when its southeastern flank lurched 50 feet seaward during a months-long eruption sequence, sliding on weak oceanic crust at rates of several centimeters per year. Stromboli in Italy suffered a flank collapse in 2002 that generated a local tsunami damaging coastal infrastructure. Ritter Island in Papua New Guinea experienced one of the largest historical volcanic collapses in 1888, when most of the island disintegrated into the sea, creating a tsunami that killed thousands. These events share a common thread: volcanic slopes built on weak foundations, subjected to gravitational forces that accumulate stress until failure occurs. Etna's seafloor displacement data suggest the volcano is more susceptible to collapse than scientists believed. The June 2025 eruption, accelerating ground deformation, and rising gas emissions all point toward a system under increasing strain. Whether collapse happens in years, decades, or centuries remains unknown, but ancient sediment layers across the Mediterranean seafloor prove it has happened before. Right now, 2 distant regions reveal the same unsettling truth. Alaska's Thanksgiving earthquake and Etna's fracturing flank demonstrate that Earth can switch from relative quiet to catastrophic activity with limited warning. The 2 systems operate through different mechanisms, one driven by tectonic plates colliding along a subduction zone, the other by a volcanic mountain slowly succumbing to gravity. Yet both share a common characteristic: stress accumulates invisibly until the threshold for failure is reached. The seismic patterns in Alaska, though not identical to 1964, share enough characteristics to warrant careful study. Etna's ongoing flank movement follows trajectories similar to those inferred before its ancient collapse, with the same southeastern sector showing the highest deformation rates and the same weak sedimentary basement allowing slippage. Yet the timeline for any future event remains fundamentally unpredictable. Scientists work to integrate seismic data, ground deformation models, and offshore geodetic measurements. Each dataset adds context to an incomplete picture, pieces of a puzzle that may never be fully solved until the moment it matters most. What scientists know is insufficient. Alaska's aftershock sequence continues to unfold, but determining whether the main shock released stress or transferred it to nearby faults requires data still under analysis. Stress transfer calculations demand detailed knowledge of fault geometry, rock properties, and pre-existing stress conditions. Etna's flank slides seaward at measured rates of centimeters per year, documented through GPS networks and satellite radar interferometry. Yet the threshold at which gradual movement transitions to catastrophic failure remains unknown. Laboratory experiments can reveal failure mechanics, but scaling those results to a mountain-sized mass of fractured lava introduces uncertainties that current physics cannot fully resolve. Statistical models suggest various probabilities for future seismic activity in Alaska, drawing on databases of historical earthquakes, but these are based on patterns that may not perfectly predict individual events. Etna's June eruption demonstrated ongoing instability, with volcanic tremor reaching very high levels and pyroclastic material collapsing from crater walls. Yet researchers cannot determine if current conditions will lead to gradual adjustment, accelerated sliding, or sudden collapse. The uncertainty reflects the inherent complexity of geological systems operating on scales that challenge our monitoring capabilities. What remains unknown could define the next disaster. If Alaska were to experience a magnitude 9 class megathrust earthquake similar to 1964, the consequences would be severe, generating tsunamis that could cross the Pacific and impact coastlines thousands of miles away. The 1964 event sent waves reaching Japan within hours, killed people in California, and permanently altered over 100,000 square miles of Alaska's landscape. A repeat today would strike a far more developed and populated region, with modern infrastructure, oil facilities, and dense urban areas directly in the impact zone. If Etna's southeastern flank were to collapse in a manner comparable to the event 8,000 years ago, millions of cubic meters of material entering the sea in a matter of minutes could recreate tsunami conditions that affected the ancient Mediterranean. Modern coastal cities from Catania to Alexandria, each home to millions, would face waves that their ancient predecessors never had to withstand. Both scenarios are geologically plausible, based on historical record. Both involve processes currently active, measurable, and documented by decades of scientific observation, yet both remain fundamentally unpredictable in terms of timing, caught in the gap between what we can measure and what we can forecast. The next significant development in either location could arrive with little warning, announced only by the first tremor or the first surge of displaced water, or the current patterns could persist for years, even centuries, without major escalation. If the Earth gave you just 1 hour of warning, what would you do?